Hello everyone, I'm Norman Wahlberger. Thanks for joining me on this adventure, talking about Hexagrammum Mysticum, but actually focusing on Pappus's theorem, where we're discovering all kinds of interesting things. I have been a little bit out of touch last few weeks. I got COVID, and actually I had to go to the hospital for 4 days. It was a little bit serious, so that's why you haven't heard much from me, but we'll make up for it. Okay, so today we're going to look at the cross ratio. Okay, this is a very important notion in geometry and one that's somewhat misunderstood. And so I'm going to give you a quick primer on cross ratios and also introduce an associated, very interesting small group called the anharmonic group, which is really a kind of a curious manifestation of the symmetric group S3. All right, so last time we were observing a remarkable duality between these 2 points, O and R, that we obtained. So we have 2 Pappus lines. One is the horizontal line, the other one is the vertical line. We have our 2 yellow points here, okay, and the pink line determined by them. And that pink line intersects the 2 original Pappus lines in points R and S. And we're especially interested in just looking at R point in the context of the 3 A1, A2, A3 original points, and in terms of this point O, which is the meet with the other Pappus line. And we discovered that there was some kind of really interesting connection between O and R. And in fact, there was actually a numerical relation that arose from some cross ratios. So here is a statement of that. Let's call it a conjecture because we haven't proven it yet. So cubic cross ratio relation. So suppose that O is the meet of the 2 Pappus lines L1 and L2, and L1 contains points A1, A2, A3. Those are sort of our initial ingredients. And that R is this meet of the pink Pappus line, which is the join of the 2 yellow points, with L1. So now we're going to define 3 cross ratios, okay, involving these 5 points, A1, O, A2, R, A3. The first one is the cross ratio of A2O and A3R. We'll call it C1. Then C2 is what you get by sort of rotating the A indices. So we get the cross ratio of A3O and A1R, and correspondingly C3 is the cross ratio of A1O and A2R. Then our claim is that these 3 cross ratios satisfy this rather remarkable but simple cubic relation, that 2 times the sum is equal to the product. So this is then an anchor that allows us to numerically or algebraically connect R and O, and so we can study this much more. Okay, so obviously we want to explore this, but let's start with a definition of cross ratio. That's a good place to start. And I'm going to do something that I don't usually do. I'm going to post something which I don't really approve of. So this is the definition according to Wikipedia, but I really want you to be aware of the difficulty here, all right? So a cross ratio is intrinsically a concept from affine geometry. Okay, so affine geometry is a prior geometry that's more elementary than Euclidean geometry or other metrical geometries. So typically we have affine geometry and we impose a metrical structure via symmetric bilinear form or a symmetric matrix. That's a way of getting the metrical structure. But it's wrong, as Wikipedia does here, to express this cross ratio in terms of distances. Okay, so they define A, B, C, D as AC times BD over BC times AD. And these quantities like AC are meant to be distances. But actually it's more subtle than that because you have to sort of take into consideration the sign. So they're talking about sort of signed distances here. They're talking with respect to Euclidean space. Okay, so I want you to very clearly, okay, appreciate that this is not the right way of thinking about a cross ratio. Cross ratio is a purely affine thing. Okay, so here is the definition that I want you to think about, okay? better definition purely from within affine geometry. So we have collinear points A, B, C, D. That's the prerequisite. Okay, we have 4 points on a line, and we are taking a cross ratio, but the cross ratio depends sort of on splitting this quadruple of points into 2 pairs of points. Okay, so there's sort of AB on one side, there's a semicolon, and there's CD on the other side. So what is the definition? Okay, it's in terms of ratios of vectors. Actually, there's 2 ratios of vectors, and we're taking the ratio of the ratio. Okay, so this first ratio is the ratio AC to BC. Okay, so these are vectors. So one of them is a multiple of the other, and so the ratio actually makes sense. Okay, it's not a question of distance. We're not measuring things. We're just taking the affine structure. And the other ratio is AD, the vector AD, over the vector BD. Okay, so you can sort of see that, this expression here involves a C. We're just replacing that C with a D to get the second expression. And it's the ratio of these ratios that is the cross ratio. Now, a pleasant aspect of this definition is that if you apply an affine transformation of the plane, that is, you translate and perhaps perform a linear transformation, then these ratios of vectors are going to be preserved. Okay? So if one vector is twice the other and they're in the same direction, and you apply a linear transformation, okay, then that new vector will still be twice the other new vector. Okay, so that ratio will be preserved. Okay, now in terms of actual coordinates, so suppose we're just actually on a line, say the x-axis, with the 4 points having coordinates little a, little b, little c, little d. Well, it's easy enough to convert these vectors into differences. So the vector AC is like C minus A, BC is C minus B, and correspondingly over here, D minus A over D minus B. Okay, and I'm replacing the colon here with an actual division. So this is now a numerical quantity, and we can sort of invert the second one to get, we can write it as a product A minus C times B minus D over A minus D times B minus C. And we observe that each one of these quantities, A, B, C, D, appears exactly twice, once in the numerator and once in the denominator. Great. Okay, so just to say that, in terms of coordinates, Wikipedia does get it mostly right. So here's also a corresponding definition in terms of coordinates, and you can see that it's pretty well the same thing, although just with a small proviso that real numbers are really not involved. You're not able to do actual arithmetic here with real numbers, so we have to get rid of this sort of adolescent point of view that we can just talk about real numbers even though we can't actually do the calculations. Okay, so everything is rational. Okay, so let us now then sort of apply this and sort of practice and have a look at an actual example. This is an example that I've looked at previously of actually specific points. So A1, A2, and A3 have coordinates -4, 3, and 7. Okay, and this line here has equation, you may remember this, here's the equation, 39,162x plus 31,841y equals 228,506. So I propose to calculate some cross ratios and to actually sort of verify that conjecture that I said. So a first order of business would be to actually define a cross ratio. So maybe I will take this thing here. Okay. So let's define. Okay, that's what we want. We might as well take the second thing. All right, there it is. But the ingredients are just going to be A, B, C, D, and I'm just going to list them as a list. A, B, C, D, although we should be mindful that there's really two sets of 2 going on here. So I'm going to make this definition, so now I have a cross ratio at hand. Okay, so what does our conjecture say? Okay, what does our conjecture say? Let me just grab that, and let's see if we can calculate these various things. So okay, so we know what the points A1, A2, A3 are. They're given by these values, which are up here, -4, 3, and 7. Now we know what O is because that's the origin, that's 0. So what about R? Well, R is going to be where this pink line meets the x-axis. So we actually have to solve something here. So let's solve something. So let's put this equation here. To get the x-intercept, we should set y equal to 0. So we'll set y equals 0. And we are going to solve for x. Okay, so that's like the R. Okay, so let's calculate some cross ratios. The first one is C1. That is R of. Okay, so A2, I may have to just copy this so I can remember. Those are the 3 values. Okay, so this thing here, maybe we'll call that R. And A1, A2, A3 like this. Okay, so which cross ratios are we talking about? We're talking about A2, so A2 is equal to 3. And then O, which is the origin, so that's 0. So that's 0. And then A3, which is 7. And then this R value, which is this thing here. Okay, and we will evaluate that. Fine. And now, our next one, something similar. C2 is going to be, okay, C2, we have to use A3 and A1. So A3 is 7, so we'll replace this 3 with a 7. And I'll replace this 7 with -4. And the O and the R stay where they are. So, okay, there's C2. And finally, C3 is, okay, so we have an A1 and an A2. A1 is -4, so that's the first one. And A2 is 3, so that's the second one. So there we go. All right, so we can actually write these things down. C1 equals this cross ratio, and C2 equals this cross ratio, and C3 equals this cross ratio. All right, so let our computer remember those. Definition, make that definition, make that definition. Okay, so now let's calculate these things. So then this thing evaluates to that, while the product of all 3 of them evaluates to exactly the same thing. The same. All right, so this gives us a confidence that we're doing the right thing. Might make this a little bit bigger so you can see it a little bit better. Okay, but it also sort of gives us a sense of the relative complexity of the story, right? These cross ratios are not entirely trivial, even though we're starting with relatively simple points. So this is not something that's, I think, close to the surface. This is a subtle business. Now there's some interesting sort of symmetry floating around here because we have these 4 points. We're organizing them into 2 pairs of points. But it turns out that the cross ratios that we can determine are are finite in number, and in fact there's 6 of them. So if you take these 4 points and you rearrange them in sort of all possible ways and look at all possible cross products that you get, then it turns out that there's actually 6 different values that you get. And here again from Wikipedia is a nice explanation of that. Okay, so if, let's say we have A, B, C, D, that's our starting point, and suppose that cross ratio happens to be lambda. So first thing to observe here, they're observing that if you interchange B and A and simultaneously interchange D and C, then it's not changing. And similarly, if you swap the C and D for the A and B, it's also not changing. Okay, so there's some sort of easy sort of permutations that you can make, which are not going to change the cross ratio. Now, if you look at other combinations, then it turns out that you get these 6 values. So if we're starting with lambda, that's the original one, then if you just interchange D and C, okay, keep A and B where they are, just interchange D and C, then you're going to get 1 over lambda. Okay, so that's a crucial property, that if you get a cross ratio just by changing the last 2, you can get the reciprocal of that cross ratio. And another important thing is this one here. If we see, to go from A, B, C, D to A, C, B, D, what we're doing is we're interchanging the B and C, replacing them with each other. Okay, the effect of that is to have the cross ratio turning into 1 minus lambda. So these 2 transformations, taking the reciprocal of a cross ratio and taking 1 minus the cross ratio, generates these other ones. So also there's 1 over 1 minus lambda, that's like the reciprocal of this one. There's lambda minus 1 over lambda. If you take 1 minus this thing here, you're going to get that, I suppose. And then you take the reciprocal of this, you're going to get lambda over lambda minus 1. And then it turns out that no further cross ratios are obtained. So there's only these 6. Now it's quite interesting because there's actually a group floating around here. Okay? It's called the anharmonic group. It's a group of transformations, essentially of a variable, which is generated by these two transformations, their reciprocation, and the lambda goes to 1 minus lambda. So if you sort of repeat those 2 operations, then you're going to get this closed group. So these 6 transformations are Mobius transformations. That is, they are all of the form sort of linear polynomial over linear polynomial. Okay, so this is a very important group in mathematics. So these are very special kind of Mobius transformations, but they're interesting because they form a closed group. And there's 6 of them. And you can convince yourself that this group is the same as S3 because there's really only one non-commutative group of order 6. But the association with the usual S3 is not at all so clear. So to make that, just give you a little bit more insight into the story, I've rearranged these 6 elements here in sort of like a hexagon. Okay, and I arranged it so that opposite vertices in this hexagon are related by the relation lambda goes to 1 minus lambda. So to go from here to here, 1 minus lambda. We take 1 over lambda, take 1 minus that, then we're going to get this one here. If we take 1 over 1 minus lambda, take 1 minus that, we're going to get this one here. Okay, so opposites here correspond to this operation, x goes to 1 minus x. In terms of the reciprocation, that's indicated by the red bonds. So these guys here are reciprocals, these guys here are reciprocals, and these guys here are reciprocals. I've also indicated in this green circle here, these are the elements of order 2. You know, the symmetric group has 3 elements which are of order 2. So you can confirm that if you do any one of these twice, you get back to where you started. These 2 elements here, this is like the identity, these 2 elements here are of order 3. Okay, they like sort of correspond to the cyclic rotations in the symmetric group. So it's quite interesting thing to be aware of. And I think as you do geometry, you should be mindful, okay, of this sort of potential richness with the cross ratio. Because if you have 4 points and you say, well, let's take a cross ratio, there's actually sort of 6 cross ratios that you could extract from this, depending on how you're going to organize these 4 points. And often things become clearer if you organize that cross ratio to be one of them rather than the other, okay? So being aware of this flexibility, being aware of this symmetry behind the cross ratio is very valuable for geometrical investigations.